Pleasure to be back. I've been back several times, but it's always very exciting. And I'd like to thank Hubert for arranging my trip and Marco for inviting me to talk. So I'll be talking about non-equilibrium dynamics of some quantum systems, and in particular, I'll put the emphasis on quantum work. I will be talking about bosons released from optical lattices. So here is an example. Initially, the bosons are held in a deep lattice, and at time t equals to 0, they are suddenly released, and they are beginning to evolve under the interacting Hamiltonian. Or another experiment where they are released, but not completely. They are still in a lattice, but the lattice is much lower, so they can hop from side to side, and they are going to form a superfluid as opposed to a Mott state as they are here. The question is, what is the quantum work done under these circumstances? So the large framework and the usual introduction, as we talked about lunch, is non-equilibrium is interesting. It's a new frontier, old, young. I mean, all of this obligated introduction. It has become very exciting in the last 15 years because of a lot of experiments that give access to questions that were asked already by Boltzmann, but now one has much more precise handle. And one of the main things is that one can create isolated systems. So let's say bosons held by lasers, they don't affect their environment, so the effects are not washed out. And one has very fine control of parameters, and one can study the systems with great precision. And many of those systems are described by integrable Hamiltonians. So what I will talk about is a particular very standard non-equilibrium protocol. It's called quantum quench. One prepares the system in one state and then evolves it. And one studies how do the properties of the system change. Let's say one prepares it in the ground state of one Hamiltonian. It has various properties characterizing it, correlation function, and so on. And then it evolves with another Hamiltonian. So for example, here it's a famous experiment, early experiment by the Greiner group. One prepares the system in a superfluid. It's really the inverse of this picture. One prepares the system in a superfluid. Here you see the condensation of momenta at 0. And then one suddenly raises the Hamiltonian, and the question is what happens to the superfluid correlations as the system evolves under a Mott-like Hamiltonian. And you can see here that the condensation disappears. We have a broad distribution of momenta, and then there is a recurrence back because the system is finite to the same original state and back and forth. Okay, so under this quench protocol, we are interested in understanding how to characterize evolution. So the Hamiltonian could be either turned out suddenly, as it's described here. You prepare it, let's say, in state A and propagate it with state B, or you can do it with a time-dependent Hamiltonian evolving with some, let's say, work parameter g of t from g0 to gt. And a lot of work was done in those last 15 years. For example, one is interested how are the local characteristics, namely local observables, how they evolve in time, how do the correlation, that raises questions of thermalization, ETH, all these very exciting concepts that relate dynamics to statistical mechanics. I will talk about another quantity, namely quantum work, which is not a local quantity, but tells us a lot about the dynamics of the system. So let me define what quantum work is. So during the quench, energy is pumped into the system. It's defined as E final minus E initial. And this is just the first law of thermodynamics because we are talking about an isolated system, so dq is 0. So here, some work is pumped into the system, which is prepared in some initial state and then propagated with the final Hamiltonian. So what is work? Unlike in classical system, here work is a random variable that involves two measurements. So the way I've set up the problem, we know what the initial state is. We know its energy. We evolve it and then do a second measurement. Now, in the second measurement, it can end up, it's energy measurement, so it can end up in any of the eigenstates of the Hamiltonian, of the final Hamiltonian, with the corresponding energy. So the initial state is phi I, energy epsilon I, with probability pi1, but the final is any of the psi n, energy En, and some probability of transition phi I overlap with psi n square. So therefore, we are going to end up with a work distribution PW. PW is going to be the sum over all amplitudes squared with corresponding energy differences to W. So PW has the form, typically in field theory in condensed matter, of what is called as a spectral function. For example, here it's an example of a spectral function in a field theory. And many of the properties it inherits just from the definition. So we have, for example, a delta function at threshold here when we begin to have, so this is an example for the case where one has excitations M. So there will be a gap, and then if you have translation invariance, you will have a continuum of excitations above it, above 2M. You can have bound states, of course, so these are going to give you delta function in the distribution, and you'll have another threshold when 4 particles begin to, the energy will excite 4 particles and so on. And delta epsilon is the difference between the ground state of the new Hamiltonian and the initial energy. So this work distribution is a directly measurable quantity. What you do is you set up the experiments, you let it evolve, you stop after time t, and you measure this, you take a measurement of the energy, and then you repeat it. And then you can tabulate the results, and you get the distribution. So it's directly measurable. It's related to many other concepts that are very interesting. There are reversible, irreversible processes, to energy production, to fluctuation theorems, Jarzynski theorem, and others. Now, work distribution is related to another quantity, which is very interesting, which is called the Loschmidt amplitude. It has many other names, return probability, survival, persistence. So you start, again, from initial state, phi I, evolve with the Hamiltonian, and ask what is the amplitude or the probability, if I take absolute value square, to find the initial state. And then it's one-line exercise to show that the work probability is the Fourier transform of this quantity, G of the Loschmidt amplitude. All you have to do is plug in a complete set of eigenstates, and then you Fourier transform it, and you get back this. So the Loschmidt amplitude probes the full Hilbert space of states. I mean, so you see from here that all states in the Hilbert space are going to intervene, and the weight depends on the overlap of those states with the initial state. So it wanders around and probes the space. And what initial state you starting? So what is very important to emphasize that it's not only the Hamiltonian matters, but also what the initial state is. Some initial state will stay around here. Some initial state will wander about in the Hamiltonian. Some states are what is called special states, and they don't thermalize, and so on and so forth. So it may happen that as the system evolves in time, there would be what is called dynamical quantum phase transition, namely if as you evolve in time, singularities would occur here in the long time limit, and then they may even recur, as you can see here in physical experiments on the quantum Ising model, that particular states would lead to such singularities. Okay, so I want to apply these concepts to the system of bosons where I release. So the first example I'll talk about is bosons that are released from a deep trap. So I have here a deep trap. I put bosons at the minima. So the initial wave function consists of product of Gaussians, and here are creation operators of the bosons in the various traps, and I release them, and then I study their time evolution. So these systems are quite well described by what is called the Lieb-Liniger model. So the Lieb-Liniger model describes boson propagating in one dimension. Here is the kinetic energy, and interacting density-density interaction. So the realization is quite standard. The experimental, one crosses lasers, and one populates it with bosons, krypton bosons, for example. C here is the coupling constant, which can be either positive, in which case the bosons repel, or attractive, in which case they attract. So this is my initial state. I evolve it in time. So I want to understand now how to do the calculation of work. So here is my quench. I evolve it in time. And now to calculate the effect of the Hamiltonian on this state, I plug here a complete set of eigenstates of the Hamiltonian, and then the Hamiltonian acts on each state and pulls out kinetic phase, and the sum n now gives me the time evolution. So the question is, what are those eigenstates n of the Hamiltonian, and how to calculate these overlaps? So the eigenstates are known since 1963. They have been found by Lieb and Liniger, and I'm writing them down here. So you see, if I have no interaction, this term is 1, and it's just product of free bosons. Now, this term introduced scattering phase shifts among the bosons. The phase shift is written down here. It's 2 arctangent x over c. So you see ki kj minus ic if xi is larger than xj, so this is 1. And if they cross each other, then the sign changes, and then I have my phase shift. So this is 1 or e to the I phi, depending on whether they cross. So this is an exact eigenstate of the Hamiltonian. You plug it in, and you show that it satisfies it. And if you want to impose, for example, periodic boundary condition, the momenta must satisfy this quantization condition, which comes from taking a boson and moving it around on a circle so that it comes back to itself. And this quantum number nj determine what the momenta is. So the momenta with periodic boundary conditions are determined by these nj quantum numbers. If there is no interaction, phase shift is 0, and then it's the usual quantization. Okay, so these are our eigenstates. And now, remember, we need the overlaps. Now, calculation of overlaps is a messy business and quite unpleasant. So it's nice if one can avoid it. So here is a claim originally put forward by Utzon, 1982, and with Gary Goldstein, with general. So Utzon put it forward for infinite volumes. Our generalization is straightforward, so it works also for finite. So what is the idea? So this is In. This is just Nn, complete set of eigenstates, and which gives us the partition of the unity. The claim is that we can replace this sum by another partition, where here it's the eigenstate, but here, if you look carefully, you see that's not a bra, but it's a Utzon state, which I've written down here. It's a parenthesis rather than a bracket. And the Utzon state is just an ordered set of exponentials without having scattering phase shifts in them. So this state is much simpler than the original ket. I can prove very elegantly that this is another partition of the unity. And now when I want to calculate the overlap and the time evolution, I have to calculate the overlap of the initial state with a Utzon state rather than with a fully fledged eigenstate. So we do that, and we can compute then the time evolution of the initial state, which is given here. So it is sum over all quantum numbers, this phase, the fully fledged eigenstate, and n is the normalization. So now that I have the time evolution, I have to calculate the overlap with the initial state. It's again a straightforward calculation. It's given by sum over all quantum numbers, exponential, and g, which is the determinant of this expression, and n is the normalization. And this expression is exact for any coupling constant, any number of bosons, and any size system. And as long as L is finite, it displays recurrences, as we expect, Poincaré recurrences, and what I will now study is the dynamics of this expression. So let me first start with the situation where the system is not completely filled. In other words, I have a lattice, but only part of it is filled. And I will talk about repulsive interaction. And to make my life easier, I'll assume that's strong repulsion, so C is very large compared to n omega. Omega characterizes the initial well. So you carry out the calculation and find this expression is sum over all permutations. The permutations keep track of what bosons have crossed each other in all possible ways. So it is sum over p minus 1 to the p e to the power minus omega p. Omega p is given by mass times delta effective. Delta effect, the original distance between two bosons was delta. Now you see it is increased effectively because of the repulsion, and it's multiplied by p. P square is given by sum over j of j minus pj. In other words, with each in permutation, this is the distance between the permutation.
Sorry, maybe I didn't understand something. So in the previous expression that the Loshmidt amplitude is an infinite sum, right?
It's no. This is. I'm sorry. I have n bosons.
All right.
So it's all the permutation of the n bosons. So it's.
But in the previous expression, is an infinite sum? The sum over these numbers.
No. That depends. If I have. Sorry.
But I mean, these numbers, they characterize eigenstates in your.
Yeah, but I have. Here I'm talking about finite number of bosons, finite size. Okay, so the numbers n have finite ranges. So this is the expression for the Loschmidt echo. And then I do the Fourier transform, and I get the work distribution written out explicitly here. And here we plot it for various number of bosons. So here is the case where we compare the effects of the interaction. So you see for large W, it's the same here. Large W characterizes short times. During short times, the bosons have not begun yet to interact because they are starting at some distance delta. It takes them a while to see each other, and then the interaction comes in and one sees the structure that emerges. So for small W's, the effect of interaction enters, and PW goes like Wn squared over 2 minus 1, as opposed to the case, to the non-interacting case where it goes like W over 2 minus 1. And that corresponds to the fact that it falls off the Loschmidt echo falls off like n power of n squared rather than n. In other words, the effect of repulsion becomes marked. And we can calculate using this distribution the average work and the exponentiated work, and one can from that connect it to Dzerzhinsky equality. If C is negative, then we have bound states of bosons. Bound states show up in the form of complex momenta that fall into pattern of n strings. And then when we use a generalization of the Utzon representation, we find that the work distribution has two parts. One consists of unbound, namely non-string momenta, and others are string contribution. So the unbound is the same expression as before. We see replaced by minus C. So delta effective now becomes smaller than delta. And this is sort of what is called a super-Tonks-Girardot expression, because there is an experiment where you suddenly prepare the system with one coupling constant and suddenly switch it, and this is the mathematical expression corresponding to it. P bound is due to the n strings, and then we get contribution on various, as a result, from different bound states. And typically these are quite suppressed, but for large C. But for finite C, this corresponds to new effects, which are quite interesting. For example, this is a contribution of two strings, and that means that we can pull out work, even negative work can be extracted. So negative work, you may be worried that it violates second law of thermodynamics, but it actually has been already considered earlier, and one can show that second law of thermodynamics is still valid even in the presence of negative work, because the average work is still positive.
Easy to understand that the contribution from string is decoupled into the contributions of separate string of various length, like if it's top level contribution to string.
Of n string, yes.
Easy to understand.
Well, you look at what the eigenstates are, and you do the computation.
Yeah, but I mean, if I'm not mistaken, an eigenstate might contain like different strings.
Exactly, it has all kind of strings. Yeah.
It's not obvious to me that they decouple, they contribution decouple.
No. So I can look at a very complicated configuration. This is when I have just two strings. But there are more complicated expressions. Okay, let us look at another circumstance where now the volume is finite, and I think about the strings, about the bosons as filling the string completely, the lattice completely. Still, it's the expression looks formally the same, but now calculating the alpha p changes. We have various permutations that are not allowed, and as a result, we will see a change in the behavior. Physically, it's easy to understand. If we have only part of space occupied, the bosons can propagate to the side and escape. But if all of them are occupied, they are much more constrained. So some results are not affected, but again, low momenta is strongly affected. Now we have all permutations contribute, and then PW falls as W to the n square over 2, as opposed to the previous expression. And as a result, the echo will fall like 1 over t to the power n plus 2, as opposed to n square. Okay. Any questions? I'm going now to the second example. Well, if n goes large, and then n goes large, and you have to take delta to 0, you take continuum limit, and you get field theory. I didn't try, but I'm imagine.
So this sum over n is something you have to evaluate?
You have to evaluate as an integral now. Yeah.
Do you know the way that the Utzon states would be related, for example, to Bethe states, which also have this representation of strings?
No, the Utzon states are precisely a way to avoid Bethe states.
There's no relation between the two representations?
No, that's exactly the point. the Bethe states are complicated. We have interaction between each two particles. If you look at the Utzon state, they are very simple here. You see? They are just they are just plane wave, and they are just ordered in space. Okay? As opposed to these states. Okay? So it's so the relation is essentially take the S matrix and make it equal to 1. Now, how to prove this identity, I can go into detail maybe later, but you can prove it very nicely.
And how general do you think holds for other intelligible
So we found Utzon representation for many other models. We found it for the Kondo, for Sine, we found it for Godin-Yang. We found it for the Heisenberg model. There are some models for which we were not able to find it, but doesn't mean that it doesn't exist. But it's in the sense finding the Utzon representation. It's like resolving the model again, because it gives you now access to quench dynamics, which is much easier. So finding Utzon representation is an important step for dynamics. More questions?
One more question. This is for the periodic case, right? So
I chose periodic case, yes.
if you have that is full, you could imagine interesting boundary effect.
So that's what I was talking about here. So I distinguished the two cases, one where the lattice was not full and one when the lattice is full, and then boundary condition constrain the propagation. And therefore, for example, so this is where I call it infinite volume, where it's not full. And here it's finite volume, where it is full. And you see difference between PW in both cases.
Probably would have different behavior in the day if you have reflective boundary.
That's a different boundary. Definitely. Actually, one can do that because we know the solution and we have to, the Godin boundary condition. Yes, thank you. Here it's periodic boundary condition in both cases, but one is infinite and one is finite. Yeah.
Sorry, now you say that there were, I thought before that you defined your roots and space as it was there. Now you're saying you have to find it to be more separately. So what's the definition of a root and space?
Well, the definition is that some identity of this kind holds. That you essentially that you can, so this is kind of product of S matrices. So where I can replace the S matrix by 1. That's
So that for XXX, for example, it will be exactly the same.
for X and X, it is it's essentially the same, but it depends on what variables you use, because the variables, momenta variables, give you an S matrix which is not pretty. So typically you change variables and then you get S matrix of the usual kind, and in those variables it's very convenient to write. Okay. So let me talk about another example. Here we are going to talk about the situation that I described before, where one talks about quenching and propagating under the Sine-Gordon equation. So I start initially with the Sine-Gordon with the mass term very, very large, and I lower it to be finite. So the mass square term can be either plus infinity or minus infinity, and I'm going to talk about two quenches, one where the bosons sit at the minimum and one where the bosons sit at the maximum. And this experiment is usually carried out and analyzed in terms of what is called the Bose-Hubbard model, but the low energy dynamics is captured by Sine-Gordon, and I will analyze the Sine-Gordon model. But there are other realizations of Sine-Gordon model, for example, as interacting condensates. There are several experimental realizations. Okay, so the Sine-Gordon model, well, is quantum integrable. It's quite ubiquitous. It describes many systems. And from my point of view, I'm going to use an equivalent formulation of it through bosonization, which makes it equivalent to the massive Turing model, which is also quantum integrable and solved, to my taste, in a much simpler way than the Sine-Gordon. And the parameters in this theory, m square and beta, are related to the parameters here, m naught and g, in a non-universal way that depends on how you introduce cutoffs and set up the system. But whatever way you set it up, there is a definite relationship. So the Hamiltonian has been studied enormously. The spectrum consists of solitons and anti-solitons with renormalized mass m. This is the unrenormalized mass. This is the renormalized mass. And for repulsive interaction, when beta square is between 4 pi and 8 pi, that's all there is. If beta square is less than 4 pi, then there are also bound states between solitons and anti-soliton, typically called breathers. The point beta square equals to 4 pi corresponds to g equals to 0, and then the system describes non-interacting fermions. Okay, so we are going to analyze it. So here we did not find a Utzon representation. So whoever asked, okay, it's not an automatic thing, and I would love to be able to do that, but we used another approach due to Destri de Vega. So they took the massive Turing model and put it on a lattice, a space-time lattice. So you have right and left movers, and they describe it in terms of spin, even and odd spin corresponding to right and left moving fermions via Jordan-Wigner. And the interaction at each vertex is given by this R matrix, which people hopefully can recognize as the R matrix of the XXZ model, which is used to solve the Heisenberg model. Of course, it's not a big surprise, but because the XXZ model is related to the massive Turing model. So the parameters that occur here, eta, which is I gamma, where gamma is defined here. So it's the interaction term, or in the fermionic language, pi over 2 plus g. And big theta is a cutoff which cuts off rapidity of the bare particle, and it's related to the bare mass, and it's taken eventually to infinity when the spacing here in space-time, delta, is sent to 0, so, and one ends up then with a renormalized mass. Okay, so notice then I have a right mover, left mover, and separated by delta, which is L over N. L is the size of the system, and N counts how many steps we have in the space direction, and M in the time direction. So time evolution, namely in this direction, in the M direction, consists of a move to the right and then a move to the left. So an elementary move consists then of product of two transfer matrices. So here we have a transfer matrix to the right, product of R matrices, which takes all these objects one step to the right, and then tau minus is going to take another step to the left. So if I want to move time t, which is m times delta, then I have to just raise this expression to the power m, and this is my time evolution operator. And now I have to decide what is the initial state I want to study. So that's the initial state I put here and here. So I'm starting here, ending up here. And I have periodic boundary condition in space. Is that clear? So the states are typically described in terms of spin, which I turn into fields via Jordan-Wigner. Okay, so here again is my geometry. I have periodic boundary condition, initial state, I propagate it, and end up, I calculate the overlap with the same initial state. So this becomes a problem in statistical mechanics, how to carry out such calculation where you have propagation. So each line corresponds now theta, eta minus theta, where I use some identity of the tau inverse moving up. And periodic boundary condition in space. Now I do a very standard trick. I turn this system on its side, and now you see time is here, and space is now this periodic condition. So we need to take a trace, but as we are evolving in time in this direction, we have boundary conditions, which originally started their life with initial and final state. Is that clear? So therefore, now the Loschmidt amplitude becomes, again, starting from it propagates me forward, but now I have a trace which I inherit from periodic boundary condition in space. And I have to calculate the time evolution in this of this animal product of t, 2j's and t minus j's, where the t's are here and are characterized by the product of these R matrices, where which give us the interaction among the propagating fermions. Okay, so now I have still to specify what are the initial conditions, or what are the boundary states under which the system propagates. And to be able to do the calculation, turns out that I need to have particular choices of states. I don't know how to do the calculation for any state. So there is a class of states for which we can do the calculation, and this goes under the name of an integrable quench. It's not enough that the model is integrable, but also the initial states has to be good enough for us to be able to calculate. So it turns out that we can do the calculation for states that are given as local products of any two lines of this form. So they are characterized by C1 and C2, actually only by the ratio up, down, down, up. When we bosonize this fermionic state, it precisely gives us either the initial state being at the bottom or at the top. So here it is then. Now, the next standard trick is when I take n to infinity. N is the size of the system I take to infinity, but in my rotated system, it projects out the maximal eigenvalue of the transfer matrix. And therefore, all I need to find is what is the maximal eigenvalue in this limit. And again, if these eigenvalues, there is level crossing that corresponds to the dynamical quantum phase transition. All right, so until now, everything was clear and could be explained. Now I have to invoke a big machinery, and you just have to believe that there is a wonderful book which appeared just in time for us to read and learn it and use the tricks. And it's called Off-Diagonal Bethe Ansatz by this group of Chinese. And off-diagonal Bethe Ansatz generalizes the more standard quantum inverse scattering to situations where quantum inverse scattering cannot be applied. For example, typically when you want to use quantum inverse scattering, you have to start with some reference state. Let's say in the Heisenberg model, even if you want to do antiferromagnets, you start from a state, the simplest state where everybody is up, and then you start flipping spins to go down. Now, such a state is not always available, and this method allows you to write what is called TQ relationships and solve it even under more generalized situation. So you open the book and get work, and you get out the following answer, that the dominant eigenvalue, lambda, depends on psi, is given by this big expression, where parameters appear, lambda, these are typical Bethe momenta, for which you have to solve Bethe Ansatz equation. So you solve this Bethe Ansatz equation, obtain these parameters, plug it in, and get this eigenvalue, and then you are happy. The parameter psi here characterizes the relationship between C1 and C2. So psi is a characteristic of the initial state. Okay, so this is very complicated. So I'll explain a neat way of going about carrying out the calculation. And that is, again, due to Destri and De Vega. They introduced an auxiliary function, which A of T psi and U, which I'm writing it out here. And the term K is written out here. It has the information about the initial state. That's psi. So if I do ground state, psi is I pi over 2. If I start from the excited state, psi is 0. And the Bethe Ansatz equation, namely, I remind you here, mean that I have to find all the values U which... Sorry. What did I do? Ah. My system doesn't. Okay. No, it's my problem. So this is Bethe Ansatz equation. It's a Bethe Ansatz equation, and every lambda must satisfy this equation, but it's a very nonlinear equation because the equation depends on its eigenvalues. So the lambdas here must solve this equation. But one can write a nonlinear equation for this quantity, and you solve this nonlinear equation, you get A, and then you have the information you need. So this complicated integral equation is nicely defined. We have here kernels, G, and here we have terms that depend on the initial conditions and the boundary conditions, and we know what integrals we have to carry out in order to capture all the solutions. So let me skip that. So what do I do? Once I have this auxiliary function, then I can write an expression for the Loschmidt amplitudes, which is given. So I know now A. I plug it into this expression here. This exponentials times log of A and A inverse, and then I obtain G. So actually all these terms that appear are quite nice. The first is E naught. This expression is the ground state energy. F here is what is called fidelity. It's the overlap, remember, between the initial state and the ground state. It's given by psi I, psi naught square. And if we compare, for example, a generic expression for the log of the amplitude, namely originally it's this expression, it stands in one-to-one correspondence with the expressions here. That is E naught T. This is the overlap which gives the fidelity, and the other terms correspond to this integral. And there are nice general results that come out of this formulation. We have, for example, strong weak duality, where gamma goes to pi minus gamma, and psi goes to I pi minus 2, and t goes to minus t. We run times backwards, and the echo does not change. And what we examine, and we see that from these particular initial conditions, we cannot have dynamical phase transition. Doesn't mean that the system doesn't have it. One has to start from different initial state. Okay, so since this is complicated,
dynamical phase transition is manifested by what?
By singularities
Of this
overlap. Yeah. Okay, so we examined that this big formulation reduces to things that we know and understand if we turn off the interaction and set beta square equals to 4 pi. Then we can solve it easily by a Bogolyubov rotation, and we see that indeed it works nicely. And then we turn on interaction. So to turn on interaction, we have to solve this equation, and we solve it iteratively. We shift so instead of working with log A, we work with eta, which is shifted with respect to the free result. We plug it in and generate term by term terms. And what we find is the following. PW is given by the expected fidelity term, where W minus delta E, that is the difference between the ground state and the initial state. And then we are close now to this threshold. We obtain, that's for W larger than delta E minus EM. Remember, that's where we are going to have generate a two particles continuum. So we get this expression, and what we find then that we have for W minus delta E close to EM, we have a singularity of square root. That is when we have, when we quench from the ground state. When we quench from the excited state, the expression is a little bit more complicated, and we find again an edge singularity, which is minus 3/2. So here it's what it looks like. PW normalized. If there is no interaction at all, namely we have just bosons, non-interacting bosons, beta square is 0, and we have a minus half singularity. When we turn on the interaction by any amount, repulsive still, then we'll have the minus half turns into a plus half. And all of them will have the same amount of exponential exponent for the close to the threshold of 2e. In a sense, beyond turning on the interaction and turning the bosons into fermions, the effect is quite minimal because we just have two bosons, a few number of bosons, so the interactions are not very effective yet. When we turn on higher, when we go to higher and higher thresholds, the effects of interactions are going to be much more marked. Now we're still with repulsive interaction, but we can quench from a maximal state, so we get other exponents, again, minus 3/2. In the attractive case, it's much more complicated. Now we have to pick up bound states and do the integrals. We get contributions. This expression is still very complicated, and we are still massaging it and trying to get simple answers, but we have not yet managed to tame it. So we are doing some other calculation for many excitations and expand G to short and long, study large deviation and effects of interaction, but this is still a work under construction. So let me conclude. Quenches are realizable and measurable, and we calculated this kind of work distribution for strongly interacting gapless system to begin with. Then we did it for lattices, Sine-Gordon model. So there are obviously many other calculations to do along these lines, and calculating many more exponents. So what our interesting question is how to relate all of this to many other issues in non-equilibrium thermodynamics, namely entropy production, fluctuations theorem. An important point is that this auxiliary function, which we used, in a sense describes non-equilibrium density of states. So its singularities would occur not only in the Loschmidt echo, but in all other physical quantities. So if you have a quantum phase transition in the Loschmidt, you would have it, it would show up in all other quantities. So one has to study it much more deeply. Again, an interesting question would be how to talk about small or large system, in which in small system fluctuations would be even more important. Quenching across critical points, defect production, and so on and so forth. How to deal with, I've discussed only sudden quenches, but of course there's a whole zoo of quenches. In particular, there is Floquet-driven quench, and which has its whole zoo of questions, which are very interesting. So, thank you very much.
Mentioned that work distribution can be measured
Mhm.
with experiments. So any actual experiments yet?
There are some experiments, but I didn't. There are some experiments in Munich in the group by Emanuel Bloch where they measured it. But they did it more for the Bose-Hubbard. But the measurement is quite straightforward, conceptually at least.
Yeah, your question. So you talked about this dynamic application as singularity of the Loshcmidt table in the picture of space-time particle mechanics model. Would that correspond to the phase transition of the
It would be a phase transition where two eigenvalues coincide. In other words, there would be another eigenvalues moving up to the maximal one. That's the usual phase transition. But this is now in time because one.
Can you distinguish between the attractive and repulsive regime by the behavior of P of W? You didn't show us curves.
I didn't show for P of,
So do you think you can?
but yeah, I showed it in the case of Lieb-Liniger.
So what was the difference?
That in the Lieb-Liniger, you have strings, so you have different distributions. You can have, for negative,
You put on an experimentalist a measure of P of W by some experiment.
yeah. Well, the simplest thing you would see that you have negative non-vanishing amplitudes for negative W.
You also had some formulas for tails, W for small W.
For small and large W, yes.
They were different.
Yes. And interacting case. That's right. Even the smallest interaction in one dimension has immediately, you cannot take the limit to 0 because the interaction modifies it completely.
Yeah. Do we know anything about the role of the initial state? And of course, your initial state is rather clear, imaginative.
So,
Non-integrable initial state. I know what that means by this.
so the physics very much depends on the initial state. So I've not seen a classification. That's what you mean, perhaps.
Well,
Uh,
in numerics also.
So, yeah, so from one state you can explore the full Hilbert space, go from one topological region to another. That is the mechanism for a dynamical phase transition. And another trajectory would not do that.
Well, I'm looking for some sort of normalization.
Uh,
Behavior of P of W.
Well, this is not directly, so when you talk about thermalization, you talk about local operators. So that's different physics. Here it's a global, these are global questions. So I'm not sure how to relate them to. These are different characterizations.
So it's a little similar, but if you have, for instance, domain wall emission condition, half field system, and in principle it would be interesting. Ask
What?
such question, and for simplest one, people can recently overlap, but for instance, in that case, energy would be infinite, and can we still define sensibly, the distribution of W?
Well, we worked on this. For example, we did it for Lieb-Liniger. a domain wall, but we calculated the current and the density that flows as a result of a quench. And what we showed is that the interaction plays a very important role in that.
Recently?
No, that is 4 or 5 years ago. Yeah. So what you find is, for example, if you fill up Thank you. So suppose you have here 0, and you fill up half of the space with bosons, and here it's empty. And at time 0, you allow the system to flow. So let's say the distance here is L. So if the system was finite, then you know in the long time limit, the density would be 1 over 2L, very simply, whatever happens. But if you have infinite, in order to have non-equilibrium dynamics, the size of the system L has to go to infinity before you take t to infinity. You cannot reverse the order of limit. And then you see that due to the interactions, you will have corrections 1 plus 1 over 2L some plus so on. In other words, you see that due to the interaction, the density is going to be diminished because the system flows, it fills space, but there is always some other room for it to expand into, and as a result, the density is reduced. Okay? If you have attractive, it would be a different situation.